Imagine you could travel back 100,000 years and hand a caveman a smartphone. He wouldn't understand it, but he'd understand one thing instantly. It's better than what he has. Now imagine doing the opposite. Take a soldier from the year 1800, hand him a sharpened rock, and ask him to go into battle. He'd laugh at you. And yet, for over 99% of human existence, that sharpened rock was the most advanced weapon on Earth. So what changed? How did our ancestors go from throwing rocks to forging blades that could cut through bone in a single swing? The answer isn't a single invention. It's a chain reaction that took thousands of years, involved a dozen different civilizations who'd never even heard of each other, and started with something nobody expected: fire. Let's rewind. Before swords, before bronze, before anything metal, humans fought with what the earth gave them for free: sharpened stones, wooden clubs, spears with fire-hardened tips. And honestly, these weapons weren't primitive in the way we imagine. Flint knappers could produce edges sharper than a modern razor blade. Some obsidian tools, in fact, are still sharper at the microscopic level than surgical steel. So if stone tools were already that sharp, why did anyone need to invent something new? Because sharpness was never the real problem. Length was. A stone blade longer than about a foot will snap the first time it strikes something hard. Stone has no give. It has no flexibility. You can grind it to a molecule-thin edge, but you cannot bend it. And in a fight, the person who can keep their opponent at a distance almost always wins. For 2.5 million years of human history, nobody could build a weapon that was both long and unbreakable. The material itself refused to cooperate. Then, somewhere around 9,000 years ago, in the ancient Near East, someone noticed something strange happening to certain green and blue rocks when they were tossed into a hot fire. They melted. That discovery, that some stone wasn't really stone at all, but metal trapped inside rock, quietly started the countdown to the first sword. This was native copper, and early humans began hammering it into beads, pins, and small ornaments. It was soft, it bent under pressure. Nobody was fighting wars with it, but it could be melted and reshaped, and that single property made it more valuable than the sharpest flint on the planet. Because for the first time, humans weren't limited by the shape nature gave them. They could design a weapon instead of just finding one. The real breakthrough came when someone, we'll never know who, mixed that copper with arsenic, almost certainly by accident, probably because the arsenic was already present in the ore they were smelting. The resulting alloy was harder than pure copper, and it could be cast into longer, thinner shapes without collapsing. In the mountains of eastern Anatolia, archaeologists have pulled real weapons from this exact period out of the ground: daggers and short swords over 5,000 years old, complete with handles, guards, and in some cases, silver inlay. These weren't crude experiments. They were finished products, made for people important enough to be buried with them. That single discovery rewrote what historians thought they knew, pushing the birth of the sword back over 1,000 years earlier than anyone had assumed. But arsenical copper had a problem nobody could ignore. It was toxic to produce. Metalworkers who spent years hammering and heating it were slowly poisoning themselves. So smiths kept experimenting and eventually landed on a safer, stronger substitute: tin. Mix roughly 1 part tin to 9 parts copper and you get bronze. Bronze doesn't just hold an edge better than copper. It's genuinely tough. It can be cast into long, thin blades that survive real combat, instead of curling like a wet stick. Bronze is the material that turned the sword from a rich man's decoration to an actual battlefield weapon. And for the next 2,000 years, entire empires would rise and fall based on one simple question: who has access to tin? That question mattered more than you'd think, because tin is one of the rarest useful metals on Earth. Unlike copper, it isn't scattered conveniently across every continent. In the ancient world, workable tin deposits existed in only a handful of places: parts of Central Asia, the Iberian Peninsula, and, strangely enough, the southwestern tip of Britain. Which means that to arm a Bronze Age army in the Mediterranean, someone had to organize a supply chain stretching thousands of miles by land and sea, moving raw ore from British mines to Middle Eastern forges. A shipwreck discovered off the coast of Turkey in the 1980s, dated to roughly the 14th century BC, was found still loaded with copper and tin ingots, cargo that never made it to its destination, frozen mid-journey for over 3,000 years. That wreck alone proved just how tightly connected and how fragile the ancient bronze economy really was, and fragile systems eventually break. Around 1200 BC, a wave of crises hit the eastern Mediterranean almost simultaneously. Drought, famine, mysterious invading fleets historians still can't fully identify, and the collapse of major trading cities that had kept the tin routes alive. When those routes died, so did the ability to make bronze weapons on a large scale. And that's the part most people get backwards about what happened next. Iron didn't take over because it was a better metal. Early iron was actually inferior to good bronze, softer, harder to shape, quicker to rust. Iron won for one reason only: it was everywhere. You didn't need a fleet of ships and a continent-spanning trade network to find iron ore. You could dig it out of a hillside near your own village. That single fact changed the shape of warfare forever. When swords required rare imported tin, only the wealthy could afford to be armed, and battles were fought by small groups of elite warriors. When the raw material was sitting in the ground behind your house, suddenly entire populations could carry weapons. Armies swelled. Warfare stopped being a contest between champions and became a contest between nations. The individual hero with his imported bronze blade mattered less. The disciplined mass of ordinary men with ordinary iron swords mattered more. Iron on its own, though, still wasn't the final answer. It needed one more ingredient to become truly dangerous: carbon. Add a small, carefully controlled amount of carbon to iron, somewhere under 2%, and you get steel, a material that is harder than bronze, more flexible than plain iron, and capable of holding a killing edge through an entire battle. Getting that carbon content right without burning the metal or leaving it too soft is one of the hardest problems in early metallurgy, and different civilizations solved it in completely different ways, without ever comparing notes. In southern India, smiths sealed iron with carbon-rich plant material inside sealed clay pots and cooked it at extreme heat, producing a legendary steel that would later be traded west and forged into blades Europeans called Damascus swords. In Japan, smiths took the opposite approach, folding and refolding raw steel thousands of times to even out its impurities, then coating the blade with clay before quenching it, so the edge cooled fast and hard, while the spine cooled slow and flexible. One blade, two completely different properties, fused into a single piece of metal. Neither group had ever met the other. Both arrived at a version of the same solution, because physics doesn't care what language you speak. By the time steel swords were common, the shape of the weapon itself had become a form of engineering. Blades were balanced down to the gram. Grooves ran down their length not for decoration, but to shave weight without sacrificing strength. The exact same principle used in a steel beam holding up a bridge. Fighting manuals from medieval Europe described footwork, angles, and named techniques as precise as any modern martial art. This was never mindless hacking. It was applied physics, refined generation after generation by people who had every incentive in the world to get the math right, because getting it wrong meant dying. And then, slowly, the sword's reign ended. Not with a single dramatic defeat, but the way most dominant technologies fade. The world simply moved on around it. Armor got too good for cutting blades to beat, so swords became stabbing weapons instead. Then came massed pikes, walls of soldiers holding spears 15 feet long against which a sword was almost useless. Then came gunpowder, and finally the bayonet, which turned every musket into a spear and made carrying a separate blade largely pointless. The sword didn't disappear overnight, it just quietly stepped aside, from a soldier's primary weapon to an officer's symbol, and finally to a museum case. But here's the part worth sitting with. Every sword ever forged, from that first arsenical copper dagger in ancient Turkey to a folded steel katana in feudal Japan, was solving the exact same equation. How do you make something hard enough to cut, flexible enough not to shatter, and long enough to reach the other person first? Different continents, different centuries, different cultures who never spoke to each other, all converging on the same answer. Because the problem itself never changed. Humans didn't just invent the sword once, they invented it independently again and again, anywhere people needed to solve the same brutal math. And every single time, the answer came down to two things: fire and the patience to keep trying until the metal finally listened.